This lesson is about types of solids, which is based on intermolecular forces. So you already know the ice floats on water and the density of ice is less than water. You already know that. But did you think why is it happening like that? The solid phase, that is the ice, expands when cooling. That also you must have noticed. So what's the reason? The unique property of water is expansion in the solid phase, right? So what may be the reason? This is because when cooling, the particles will have lower energy and therefore more order, and hydrogen bond overweighs the freedom of movement. You know, even in liquid water there is hydrogen bonding, but since it is at a higher temperature it will have more energy to move around, so the hydrogen bond is not that predominant compared to the hydrogen bonding in ice. Since it is at lower temperature, less energy, and hydrogen bond overweighs the movement, and it takes the shape of hexagonal shape like shown here. So when there is hexagonal shape orderly arrangement, what will happen is the volume will increase. When the volume increases, the density decreases. That's why ice floats on water. So we call this orderly arrangement, this type of solids, we call it as crystalline solid. If there is an orderly arrangement internally and externally, it is called crystalline, like shown here. And if it is not, we call it as amorphous. So here are the characteristics of crystalline and amorphous solids. There are two types, as I just mentioned. That is, if there is orderly arrangement of particles, repeating pattern, and if it is predictable, we call it as crystalline. If not, random arrangement of particles, not repeating pattern, and not predictable, we call it as amorphous. You can see the pictures here. Some other crystalline substances are metals and ceramics. So in crystalline, you can see that mostly, you see that orderly arrangement. Whereas in amorphous, it is glass, one example. It is not orderly arranged. You can see that here. And high density polyethylene jug, that is the milk jug and all, is made of in between some crystalline part and some amorphous part. We call it as semi-crystalline. That mostly we can say amorphous with the regions of crystallinity that is used for temporary storage of materials. So based on the position in the periodic table, we can classify solids in different forms. Different solids are there. Metals form metallic solid, metals and nonmetals form ionic solid, nonmetals form molecular solids, and fourth group form covalent network solids, and atoms form atomic solids. So the first one, as we already discussed, is the ice, which is having London dispersion forces, dipole-dipole, and hydrogen bonding. And the particles in the solids are more, we can say molecules with the non-metals at the different locations here, crystalline lattice. So the molecules can be polar or non-polar. They are poor conductors with a low melting point because you already know that is covalently bonded. And this is an example of ice here. Sucrose, the structure of sucrose, solid carbon dioxide, the molecular representation of solid carbon dioxide. So these are called molecular solids, which are made of nonmetals. Another type is ionic solid, which you are familiar with, one metal and one nonmetal. So metal form cation and the nonmetal form anion. Anions are bigger and cations are smaller. So the attraction between them depends on the Coulombic force, which is the charge on both ions divided by the distance between them. And this is shown as sodium chloride here. And it has high melting point, and it's not good conductors in the solid state, but it's a good conductor when it is liquid form or in the aqueous form, because the ions are easy to move if it is in aqueous solid form. Another thing I want to tell you here is these are brittle. what is the meaning of brittle is, see these ions here, when you apply pressure on it, what will happen is the anion and cation, it will relocate and the same ions will take the position. And what will happen here is the same charges, this is positive and this is negative, right? So what will happen is it will repel and it is easy to break through the cleavage over there. That is why it is so brittle. Ionic solids are brittle, you can break it very easily because of that movement of ions. Another type of solid is atomic solid, and the particles are atoms held together by LDF. They are poor conductors with a low melting point, and examples are mostly from the 18th group, argon, krypton, etc. Another type of solid is the vast network of covalently interconnected atoms. The properties depends on the structure. These are normally from fourth group elements, carbon, silicon, etc. and they have 4 valence electrons and can form a large network structure. So for example, here you can see for carbon there are 2 forms shown here. One of them is graphite and the other one is diamond. Graphite is soft, you are using in pencil lead, so you can write with that pressure itself, it is sliding over each other. Such a weak force is in between the hexagonal structure here. Whereas here you can see tetrahedral structure which is very hard, which is shiny and do not conduct electricity. This one graphite conduct electricity, diamond do not conduct electricity. So these two forms of carbon, we call it as allotropes. So allotropes are different forms of the same element with the different properties. So this is another example of covalent network compound, which is silicon dioxide, which is also very hard, it's insoluble. So here the thing I want to talk about is doping. So in the case of doping, what is happening, let me see. And also, you know what, in silicon chips in computer is also from this group, fourth group, used in computer. And so let me go back to the doping, that is the fourth group elements. Let us take the same example, silicon. When you combine that one with the element which is higher in group, which is fifth group, if you combine that one, what will happen here is arsenic is coming with another extra electron and it will start conducting. So which is called n-type because the electrons are negatively charged, so we call it as n-type. But at the same time, if you combine silicon with another element which is third one, boron, let's take boron. So which is coming with a less number of electron, so that means more positive charge, so we call it as p-type semiconductor. Both are conducting little bit. That process is called doping. Okay, so that's all about this covalent network solid. And now the last one is metallic. Of course, from the word itself it is clear, so the metals form metallic bond. So metal cations in a diffuse delocalized electron cloud. What is that means? Let me explain. And they are good conductors of heat and electricity. They are malleable, they are ductile, and the melting point varies. So let's see in detail that one. Here you can see that metals are good conductors because these electrons can move around in the lattice, and the cations are there and the electrons are moving around just like C. So we call it as electron C model. So electrons are able to gain kinetic energy in hotter areas of the metal and are able to quickly transfer it to the other parts. So that's the reason for conductivity. Thermal conductivity and electrical conductivity is because of the movement of electrons. And now metals are malleable and ductile rather than brittle like ionic compound as a result of the non-directional nature of metallic bonds. The attractive forces exerted by the positive metal ion for the mobile electron occur in all directions. This means that layers of atoms can move, means it can slide over each other without disrupting the force between the positive ion and negative electrons. So here it is. So it can easily move, that is why it is malleable and it is ductile. It can slide over each other. In a very simple way, we can say that. Okay, the reason for high melting point is the attraction between those electrons and the positive kernels or positive cations. These are the properties we already discussed, but it's a summary of that. So metals do not bond with another metal, as you know, but it form alloys. It is a homogeneous mixture which is also known as solution. There are two types of alloys we are talking about. One is substitutional alloys and the other one is interstitial alloys. In substitutional alloys, so it will replace one of the atom with another atom. So it should be same size. That is the way you can identify. So that is called substitutional alloys. Whereas in interstitial, it is going in between the already arranged atoms. So that it is occupying the empty spaces. That is what is called interstitial. So definitely it should be smaller than the atoms already there. That's the way you can identify.